Welcome back to the third video in our weather app series. So far, we've built onboarding and the settings screen, and we've integrated APIs from two sources, weatherapi.com and openmedio.com. We use two APIs because the free tier of weatherapi.com provides a 3-day forecast, and we need a weekly or up to 10-day view. We also integrated maps, styled it with a monochrome theme, and added the Places SDK autocomplete. In this part, we'll continue building our app. We'll build the current weather screen, the weekly weather screen, a home screen with bottom navigation, so stay tuned and let's get started. Before we build the screens, we need a small change in the data module. Open repository module and add this binding. @singleton keeps one instance of the repository for the app. Binds maps the interface to its implementation at compile time. Next, update the network module. First, change provide HTTP logging interceptor to return HTTP logging interceptor and set its level to body so you can see full requests and responses in the logcat. Then update provide OK client. Drop the cache and the application context since the repository layer now handles caching. Keep the timeouts, add base URL interceptor to rewrite the base URL, and add the logging interceptor to record the final request and response. Next, update database module. Change provide database repository to accept cache in the constructor and pass it to database repository impl. Open database repository impl and add the new cache parameter to its constructor. Update insert location and set current. Call cache.clear before inserting the new location. This ensures when a user changes location, any existing cache data is dropped, so we don't show data from the wrong place. Update the read path from get all locations first to get current location. This returns only the active location instead of a full list. Then change the toLocation model extension to return a non-null location model. Make sure the entity fields you map are non-null or provide safe defaults so callers always receive a valid model. Next, we'll update several DTOs starting with air quality, current, day, location, weather API forecast DTO, and a few others. The main change is to align some JSON keys with the latest response and switch certain numeric fields from int to double. I'll make these edits now and then we'll move to the next section. Next, update weather forecast model and weekly weather forecast. We're adding two fields, zone and local epoch. We also update a few return types and introduce the new future moon phase model. Similarly, add a new units data class inside weekly weather forecast so we can read unit info from the server and map it into the domain model. Next, we will create the current weather extension Kotlin file, and then we convert the weather DTO into a domain model. First, we grab the first forecast day and its astro block, then read the current conditions. Next, we choose units from the isMetric flag. We set temperature, wind, and pressure units. We compute display values, temperature, feels like, wind speed, pressure, and dew point from either metric or imperial fields. We also map future moon phases by walking each forecast day and pulling the date, phase, and illumination. Finally, we build weather forecast model. We fill location, time zone, and local epoch. We set isDay, temperature strings with units, condition text and icon code. For hourly details, we map each hour to time, epoch, integer temperature with units, icon code, and rain or snow chance. We add humidity, dew point, pressure value with a separate unit, wind speed string with unit, wind direction and degree, air quality index, sunrise and sunset, moon times and phase, and the future moon. Next, we will create the weekly weather extension file under the mapper package and write the extension function to weekly weather forecast DTO to weekly weather forecast. First, create a daily data map to hold each day's summary. And next, build the units object from the server's unit fields so the UI knows how to label values. Then prepare an hourly forecasts by day map because we'll group each hour into its day bucket. Now loop over hourly.time with for each indexed. For each hour, create a calendar in the API's time zone, snap it to midnight, and compute the day's epoch in seconds. With that index, build an hourly forecast by pulling values from all the hourly arrays at the same position and add it to the list for that day key using get or put. After that, loop over daily.time with for each indexed and read the max min temperature and the max wind for the day. Use the time value as the day key, create a daily forecast with the daily fields, attach the matching hourly list from hourly forecasts by day, and store it in daily data. Finally, return a weekly weather forecast that includes daily data and units. Next, update weather repository. Change get current weather to return a result of type weather forecast model and get weekly weather to return a result of type weekly weather forecast. Then open the weather repository implementation class. In the get current weather function, update the mapper lambda to call the new to weather forecast model extension. In get weekly weather, update the mapper lambda to call to weekly weather forecast function. We will slightly change the query params to add more query parameters. That is the only change here, and the rest of the flow stays the same. Open user settings repository impl and add a private cache field of type local cache. This gives the repository a simple in-memory store for computed results. Next, go to the save units function. Right after you persist the new unit choice, call cache.clear. Local cache.clear removes everything the app cached under the old units, so the next read forces a fresh load and the UI reflects the new labels and conversions immediately. We are not changing how callers use the repository. We are just making save units responsible for invalidating data that it makes outdated. Next, open the data modules build.gradle and, inside the plugins block, add the Kotlin serialization plugin. This wires in the Kotlin X serialization Gradle plugin using your version catalog, so you get compile time codegen for @serializable models without extra setup. Hit sync, and you're done. Let's make location lookups cleaner and set up the use cases your UI will call. Start by opening your location lat-long data class and add a new function named toQuery. This function returns a single string with latitude and longitude separated by a comma. Next, go to the domain module. Inside the UseCase package, create a new subpackage called weather, then add two classes, getTodayWeather UseCase and getWeeklyWeather UseCase. Each use case should expose a simple function you can call from your Viewmodel. GetTodayWeather UseCase uses constructor injection and injects weather repository for network/data access, database repository for the user's saved location, and user setting repository for preferences like units. The suspend operator fun invoke makes the class callable like a function from coroutines. Inside, it pulls the current location from the database, grabs its latling, and turns it into a single latitude-longitude string via toQuery. It then reads user settings and checks if the selected unit's enum is metric to decide between metric and imperial. With those two inputs, it calls repository.getCurrentWeather, passing the query string and the unit flag. The repository returns a result, so errors and successes are handled in one type. GetWeeklyWeather UseCase fetches the weekly forecast for the saved location. Hilt injects weather repository, database repository, and user setting repository. The invoke function reads the current lat long, formats it with toQuery function, checks if units are metric, then calls repository.getWeeklyWeather, and returns a result of type weekly weather forecast. Next, we'll update the UI kit and add Lottie for Compose so we can play lightweight JSON animations in our weather screens. Open the UI kit module's Gradle file, add the Lottie Compose dependency, and sync. Now let's bring in the weather icons. Open Resource Manager, click the plus button, choose Import Drawables, and select the Pack1 assets you've downloaded from the repo linked in the description. Import the whole set so names stay consistent. Android Studio will copy them into res drawable lay. Now add two Lottie JSONs for loading and error. Use the ones you downloaded from the official Lottie site and place the files in the raw directory. Keep the exact file names we're using so your resource lookups don't break. Next, go to the UI kit module and create a package and name it dialog. Inside that, create a file and name it as loading dialog. Loading dialog is a small modal you show while work is in progress. It takes a Lottie composition spec so you can point it at any Lottie JSON. Remember, Lottie composition loads and caches the animation, and animate Lottie composition as state drives its playback. The dialog itself is non-dismissible, which means the user can't close it. You hide it by not composing it anymore. Inside, a box centers the content and gives it a 100 dp square, white, rounded container with 8 dp corner radius, which keeps the spinner readable against any background. Lottie animation renders the loaded composition and uses the animated progress value to play it smoothly. Jump into the app module and create a new package for the current weather feature inside your existing feature package. Inside that, add 3 child packages: UI Model, UI Mapper, and Composable. UI Model will hold lightweight data classes tailored for the screen, separate from your domain models. UI Mapper will convert domain models into those UI models so the composables only deal with display-ready data. Now open the Composable package and add 2 sub-packages, component and items. Use components for the smallest reusable UI piece. Use items for composite views that stitch components together. Next, let's create the current weather UI model file. Current weather UI model is the single object the UI needs. It bundles a hero section, an hourly weather list for the timeline, a weather details list, and a next 3 hours rain list for rain chances. Hero section holds the basics you see at the top: the location name, a plain text condition, a drawable icon, and a temperature string. The icon is marked with @drawableRes so the compiler catches wrong resource types. Hourly weather repeats a small unit of data for the timeline with a temperature string, a drawable icon, and a human-readable time. Weather detail is a sealed class, so one list can carry different detail cards while staying type safe. Humidity stores humidity and dew point as strings and exposes humidity percentage, which parses 85%, into a 0 to 1 float for progress arcs. Pressure carries the label value, the numeric pressure, the unit, and a reasonable min-max range for gauges. Wind includes speed, a compass direction label, and wind degree, plus a rotation float you can feed straight into a compass arrow. Aqui takes a single AQI value and maps it to a friendly quality label, a 0 to 1 percentage for meters, and a color to theme the chip. Sunrise, sunset, and moonrise, moonset keep both the formatted times and their epoch values, along with the current local epoch, so you can compute progress across the day or night without extra conversions. Moon phase is a simple pair of phase value for drawing and phase name for the label. Next, hours rain gives you the time slot and a percentage for quick rain chips. With these models in place, your composables can focus on layout and animation. And we'll start with the helpers. First, getWeatherIcon maps the provider's icon code to the right drawable, switching between day and night versions with the isDay flag. Then TimeString2Millis takes a string like 6 to 9 a.m., parses it with DateTime formatter builder using a case-insensitive pattern, combines it with today's date in the given zone ID, and returns epoch millis. For hourly labels, we use to hour and minutes, which reads the input with simple date format and formats it thenon. With those in place, we implement TUI model to turn weather forecast model into the single object the screen needs. We compute epoch now from local epoch and build the weather details list, humidity and dew point, pressure with both a formatted label and a numeric value, wind with speed, direction, and degree, AQI plus sunrise, sunset, and moonrise, moonset. For the time cards, we convert the provided strings to epoch millis with TimeString2Millis using the API's zone, so progress visuals line up with local time. We collect moon phases by adding the current phase, then mapping future phases into simple value and name pairs. To power the next 3 hours card, we locate the first hourly item after now by parsing each item's timestamp with from hour and minutes to date, then take up to 3 entries from that index. Finally, we return current weather UI model. The hero section shows location, condition text, temperature, and an icon from getWeatherIcon. The hourly weather list maps each row to a tiny model with temperature, a resolved icon, and a display time from to hour and minutes. We pass through the assembled weather details and moon phase list, and we prepare next 3 hours rain as time and percentage pairs taken from those next hourly entries. The result is a clean UI model with all formatting and time math done once here, so the composables can stay simple. We're creating currentWeatherContract.kt inside feature/currentWeather. This file defines the contract for the screen, which user events we accept, which one-off effects we can fire, and which states the UI can render. UI event is a sealed interface with 3 entries. On start, on search, and on weekly forecast UI effect is for single-shot actions that the UI should perform and forget. Navigate to add new location and navigate to weekly weather are both declared as data object. UI state models what the screen can show. Today's weather carries a current weather UI model, which is the display ready data. Initial is the empty state before we load, and error is a simple failure state the UI can react to. Next up, we're creating currentWeatherViewModel.kt, then wiring it up to fetch data and drive navigation. At the top, we mark the class with @HiltViewModel and inject getTodayWeather UseCase, so Hilt can provide the dependencies for us. We keep internal state in a mutable state flow that starts at UIState.initial and a mutable shared flow for one-off effects like navigation. Both are exposed as read-only with asStateFlow and asSharedFlow, so the UI can observe without mutating. The Viewmodel exposes a single event function that takes a UI event. When onStart arrives, we call launchVM to run a coroutine in the Viewmodel scope and execute getCurrentWeather UseCase. The UseCase returns a result, so we call fold. On success, we map the domain model to a screen-ready model with ToUI model and update the state to UI state today's weather. On failure, we switch the state to UI state.error. For onSearch, we don't touch the main state. We emit a one-time effect navigate to add new location using emit effect so the UI can navigate without re-rendering content. For on weekly forecast, we emit navigate to weekly weather in the same way. The result is a clear MVI loop. The UI sends events, the Viewmodel does the work, state updates drive the screen, and effects trigger navigation, all with structured flows that are safe and easy to test. Let's drop a new file into the component and call it arcprogress.kt. ArcProgress is a reusable progress ring built with Canvas. You pass in a progress value and it clamps it to max so it never overshoots. The look is configurable. Arc angle controls how much of the circle we draw. Progress width is the stroke thickness, and you can set separate colors for the filled and background arcs. There's a content slot centered on top so you can overlay a label. By default, it shows the integer progress. Inside the box, the canvas takes the full size and converts dp to pixels for padding and stroke width, so the arc doesn't get clipped. It builds a rect that leaves room for the stroke on all sides, then computes the start angle as 270 minus half the arc, so the ring is centered at the top. The background arc is drawn first across the full arc angle with a rounded stroke cap for smooth ends. The progress arc comes next only if progress is greater than 0 and its sweep is a fraction of arc angle. calculated as progress divided by max. Because both arcs share the same bounds and start angle, the filled segment sits perfectly on top of the track. Finally, the box centers your content composable over the ring so text or icons stay aligned. The preview shows how to wire it up in the theme. It wraps the composable in weatherwise theme, sets a surface background so contrast is correct. It also demonstrates swapping the default label for app text and uses content color for to pick a readable text color against the surface. This gives you a self-contained progress indicator that's easy to style and drop into cards, detail rows, or headers. Let's add a new file named error component. We're building a reusable error UI as a composable that shows a Lottie animation, a title, a short description, and a retry button. The function takes a Lottie composition spec so we can point it to any JSON animation, plus strings for the title and description, and an onRetry callback. At the top, remember Lottie composition loads and caches the animation. The layout is a column that fills the screen and centers everything both vertically and horizontally. Inside the column, Lottie animation renders the composition at a fixed 250 dp box. Spacers add breathing room between elements so the layout doesn't feel cramped. The first text uses headline medium for a clear title, and the second text uses body large with centered text and horizontal padding to keep longer messages readable. Finally, the button wires to onRetry. Tapping, it lets the caller trigger whatever recovery flow they want. Start by adding generic infocard.kt under the component package. The first generic info card is a flexible 2-column card. It takes a title plus 2 lambdas, left content and right content, both scoped to row scope so callers can use row modifiers like weight if they need. The card sets a light 1 dp elevation and an aspect ratio of 4:3, which makes it behave like a tile that stays consistent in a grid. Inside, a column with 16 dp padding lays out the title at the top using app text. Below that, a row fills the remaining space, centers content vertically, and uses space around so both sides breathe evenly. Finally, it calls left content and right content, letting the caller render 2 balanced blocks within the same card. Below it, we add an overload of generic info card for the common icon, title, then content layout. This version fills the width and wraps height. The header row shows an icon next to the title, with a small spacer for separation after a 16 dp spacer. It invokes the contents lambda to render whatever the caller needs, like a value row or a small chart. This keeps a single place for card chrome while letting the inside stay completely custom. Next, let's make the moon phase like the thin crescent, the half moon, the full moon, and everything in between. This is a composable function that renders moon phases using Canvas. It takes a surface angle parameter from 0 to 360 degrees, where 0 is the new moon, 90 is the first quarter, 180 is the full moon, and 270 is the last quarter. First, we set up the canvas with a match parent size modifier. We calculate the padding, diameter, and create a rect for the moon's bounds. Then we get the center point and radius. We also convert the line width from dp to pixels. I'm defining 2 helper functions here, draw light circle and draw dark circle, just to avoid repeating code. They draw full circles in light and dark colors respectively. Now we normalize the angle using modulo 360 to handle values outside 0 to 360 range. Here comes the main when block that handles each phase. For a new moon at 0 degrees, we simply draw a dark circle. For waxing crescent between 0 and 90 degrees, we start with a light circle as the base. Then we draw a dark arc covering the left semicircle using start angle 90 and sweep angle 180. Now here's the key part. We calculate half width using cosine of the normalized angle. This gives us the width of the elliptical shadow. We create a foreground rect centered horizontally with this calculated width, then draw another dark arc to create that curved terminator edge. At exactly 90 degrees for the first quarter, we draw a dark base circle, then overlay a light arc on the right half using start angle 270. For waxing gibbous between 90 and 180, we reverse the approach. Dark base circle, light right half, then calculate half width using sine of angle minus 90. This time we draw a light arc to bulge out the illuminated portion. A full moon at 180 is straightforward, just a light circle. For waning gibbous from 180 to 270, we mirror the waxing gibbous logic but with opposite sides. Dark base, light left half using arc starting at 90 degrees, then cosine calculation for the width and a light arc to complete the shape. Last quarter at 270 is the opposite of the first quarter, dark base with light left semicircle. Finally, waning crescent uses the same technique as waxing crescent but mirrored. Light base, dark left half, and cosine of 360 minus normalized angle for the width calculation. After the phase drawing, we add the terminator line. For crescent phases, we draw a dark vertical line down the center. For gibbous phases, we draw a light line. This enhances that straight edge where light meets shadow. Lastly, we draw the outer stroke circle using stroke style to give the moon a clean boundary. This must use the exact same center and radius as our moon rect to align perfectly. And that's it, a complete parametric moon phase renderer that smoothly transitions through all lunar phases based on the input angle. SunMoonViewComposable function renders a sunrise or sunset arc with a moving icon, like showing the sun's path across the sky. It takes start time, end time, and current time to calculate progress along an arc. First, we define a constant arc-squark angle set to 160 degrees. This determines how wide our arc will be, not a full semicircle, but 160 degrees of it. The function parameters include timing values, colors for the arc line and background, a root color for gradients, theme flag, and an optional icon painter that will move along the arc. We also have size parameters for the line width, dotted background line, and margins. I'm defining two shadow alpha factors here, 0.1 for light theme and 0.2 for dark theme. These will be used later to create that subtle shadow effect below the arc. Now we calculate the progress. Max progress is the total duration from start to end time. Progress raw is how much time has elapsed. We use coerce in to clamp the progress between 0 and max so it doesn't go negative or exceed the range. Setting up the canvas with match parent size. We convert all our DP values to pixels, margin, line size, and dotted line size. The width px is our drawing width minus margins on both sides. Here's some geometry. We calculate delta radians using the angle difference between 180 degrees and our arc angle divided by 2. This helps us figure out the radius needed so our arc fits exactly within the width. The formula is width divided by 2 divided by cosine of delta radians. This ensures the arc endpoints touch the edges of our canvas width. We set center x to half the canvas width and center y to margin plus radius. This positions the arc's center point vertically so the arc sits nicely in our view. Creating an arc rect that defines the bounding box for our arc. It's centered horizontally and positioned vertically based on our calculated center point. Now for the shadow colors. We multiply the line colors alpha by our shadow alpha factor to get a semi-transparent shadow color. Then we create a gradient with two colors, a more transparent version at the top and the root color at the bottom. This gradient goes from the arc's top to the bottom of the canvas minus margin. Calculating angles now. The start angle is 270 minus half the arc angle. This positions our arc to start from the left side. The progress sweep angle is the proportion of progress multiplied by the arc angle. The progress end angle is where our progress currently ends on the arc. Here we call a custom draw shadow function passing the arc rect, progress end angle, our gradient shader, and line size. This draws that soft shadow beneath the progress arc. Next, draw the background dotted arc line using the background color. This uses the full arc angle as a visual guide showing the complete path. The style is stroke with our thin dotted line width. If progress is greater than 0, we draw the actual progress arc on top. This uses the line color, starts at our start angle, and sweeps for the progress sweep angle. The stroke width is thicker here, our main line size. Now for the icon positioning. If we have an icon painter and progress is greater than 0, we need to place the icon at the current progress position on the arc. First, calculate the delta angle as the progress end angle minus 180. Then use cosine and sine to get the x and y offsets from the center. We take absolute values and multiply by half the arc width to get the actual pixel distances. For icon offset x, we check if the progress end angle is less than 270. If it is, we're on the left side of the arc, so center x minus delta width. Otherwise, we're on the right side, so center x plus delta width. In both cases, subtract half the icon size to center it. The icon offset y is center y minus delta height minus half icon size. Using translate to move our drawing context to the icon position. Then rotate by the icon rotation parameter around the icon's center pivot point. Finally, draw the icon painter with the specified icon size. Draw shadow function creates a soft shadow effect using layer blending. We create an Android rectf that's the top half of our arc rect from the top to halfway down. This is the clipping region for our shadow. Setting up an Android paint object with anti-aliasing enabled, stroke style, and our stroke width. Using draw into canvas to access the native canvas. We call save layer with our rect and paint. This creates a new drawing layer we can manipulate with blend modes. First, draw the full arc using our gradient brush. This draws the entire 160-degree arc with the shadow gradient. Now here's the clever part. We clear the portion beyond our current progress. Calculate clear x as the center x plus the cosine of 360 minus progress end angle multiplied by half the arc width. This gives us the x coordinate where we need to start clearing. We draw a transparent rectangle from that clear x position to the right edge of the arc using blend mode.clear. This erases everything to the right of our progress, leaving only the shadow beneath the actual progress arc. Finally, restore the canvas to its previous state using restore to count with the layer ID. And that's it, a complete sun or moon arc visualization that shows progress over time with a moving icon and a subtle shadow effect beneath the progress portion. The arc stays fixed at 160 degrees, the icon moves smoothly along it, and the shadow dynamically follows the progress. This is a composable function that creates a hero section for a weather app. You know, that prominent header area showing current weather with a background image. It takes a hero section data object and a navigation callback for the location search. We start with a box using wrap content size and a fixed height of 200 dp. The first layer is an image using a background resource. The modifier chain here is important. Fill max width makes it span horizontally, then ignore horizontal parent padding with 16 dp. This is a custom modifier we'll define later that lets the image extend beyond the parent's padding. Next, we add another box with a semi-transparent black background. This creates that darkened overlay on top of the image so our white text remains readable. Now the content column with 16 dp padding. This holds all our text and icons. Inside, we have a row with center horizontal arrangement and center vertically alignment. First element is an image showing the weather icon, then a spacer for breathing room. Next, a nested column containing two app text components. The first shows current weather condition using title medium text type. Below that, the location name using label small type. We add a spacer with a weight 1. This pushes everything to the edges, icons and text on the left, search button on the right. After the row, we display the temperature as an app text with display medium type. This will be large and prominent. Now for the custom modifier function, ignore horizontal parent padding. This is a layout modifier that allows a child to escape its parent's horizontal padding. Inside the layout lambda, we receive the measurable child and constraints. We calculate override and width by taking the max width from constraints and adding 2 times the horizontal padding value converted to pixels. The multiplication by 2 accounts for both left and right padding. We call measurable.measure with modified constraints, copying the original but overriding max width with our calculated value. This tells the child it has more space than the parent actually allocated. In the layout block, we simply place the placeable at 0, 0. The child thinks it has more width, so it extends beyond the parent's bounds. This is a composable function that displays a horizontal scrolling list of hourly weather forecasts. It takes a list of hourly weather objects and a one-click callback for the weekly forecast button. First, we create a remembered lazy list state. This maintains the scroll position of our horizontal list across recompositions. We start with a column mana. This will stack our title, card with hourly items, and button vertically. The first element is an app text showing the section title. We get the string from resources, add a 16 dp spacer for vertical spacing below the title. Now we create a card component with 2 dp elevation. Inside the card, we have a lazy row. This is the horizontal scrolling list. We pass in our remembered list state to maintain scroll position. In the lazy rows items block, we iterate through the hourly weather list. For each item, we call hourly weather item, passing the individual hourly data object. After the card, another 16 dp spacer for breathing room. Then we add an app button for the weekly forecast call to action. Now let's define the hourly weather item private composable. This is marked private because it's only used within this file as a helper component. It's a column with vertical arrangement center and horizontal alignment center horizontally. This centers all content both ways within each item. The first element is the temperature displayed using app text with body medium type. Then an image showing the weather icon. We use painter resource with the icon from hourly data, and we provide a content description for accessibility. Finally, the time displayed using app text with label small type. This would show something like 2 p.m. And that's it, a complete hourly weather section with a title, horizontally scrolling card containing weather snapshots for each hour, and a button to navigate to the full weekly forecast. MoonPhaseItem composable function that displays multiple moon phases in a card layout. It takes a list of moon phase objects as a parameter. We start by calling generic info card, which is a wrapper component that provides consistent card styling across the app. We pass it a title moon's phase. The trailing lambda contains our content. We create a row with a basic modifier. This will lay out our moon phases horizontally side by side. Inside the row, we use for each to iterate through the moon phase list. For each moon phase object, we create a column. The modifier includes weight 1. This is crucial because it makes each moon phase column take up equal space in the row, dividing the width evenly among all phases. We also set horizontal alignment to center horizontally, so the moon icon and label are centered within each column. Below the moon visualization, we add an app text component displaying the phase name from our data object. Rain chance item. Composable displays rain probability for the next 3 hours. It takes a list of next 3 hours rain objects. We wrap everything in generic info card with a title. Inside, a column with top arrangement holds our rain forecast items. We for each through the next 3 hours rain list. For each item, create a row that fills max width with padding and center aligned vertically. The first element is the time displayed as label small text. Next, a linear progress indicator showing the rain percentage. The progress lambda converts the percentage to a float between 0 and 1 by dividing by 100. The modifier uses weight1 to fill available space between the time and percentage labels. Finally, display the percentage value with a percent sign using label small text type. That's it, a simple list showing time, visual progress bar, and percentage for rain probability over the next 3 hours. All right, next we will cover the weather detail components, starting with humidity item. This takes a humidity model and wraps it in generic info card. The left content shows humidity value and dew point using the right content helper. The right content is a vertical progress bar. We create a column with weight 1 and center alignment. Inside, we show 0 at top and 100 at bottom labels. Between them, a box with 12 dp width, rounded corners, and amber background color. We rotate it -180 degrees to flip it. Inside that, another box fills to the humidity percentage height in yellow color with rounded corners. This creates a thermometer-style vertical fill indicator. Next, pressure item. Similar card structure with left content showing pressure value and unit. The right content uses our custom arc progress component, an arc with progress 80 out of 100 max, arc angle 288 degrees, tertiary theme color for progress, light gray background, and aspect ratio 1 to keep it square. Moving to wind item. The left content shows wind speed and direction. The right content displays a wind direction graph image. We then apply graphics layer rotation from the model, then rotate 180 degrees. Now, AQI item for air quality index. The left content shows quality text like good and for most people. The right content uses arc progress again. The progress color comes from the model based on AQI level. The content lambda inside displays the actual AQI numeric value. For sunrise set item, we use the full card content lambda instead of left-right split. Inside a column, we place our SunMoonViewCompose component, that arc we explained earlier. We pass sunrise and sunset epochs as start and end times, current time from the model. Below the arc, a row with space between arrangement shows sunrise time on left and sunset time on right. Moonrise set item also uses full content lambda. A row with space between arrangement contains a column on the left showing rise label with moonrise time, then set label with moonset time. On the right, we display a moon icon at 72 dp size with slight transparency. Finally, the right content helper function. This is a receiver function on row scope, so it has access to row weight modifiers. It creates a column with weight 1, center vertical arrangement, and start horizontal alignment. That's the complete set of weather detail cards. Humidity with vertical bar, pressure with arc, wind with directional indicator, AQI with colored arc, and sunrise sunset plus moonrise moonset with their respective visualizations. Starting with current weather screen composable. This is our screen level component taking 2 click callbacks, one for general navigation and one for search. We get the view model using HILT Viewmodel from HILT dependency injection. collect the UI state as a state object using collectAsState, so we recompose when it changes. Immediately trigger the onStart event to load data. Now we handle the UI state with a when expression. If the state is today's weather, we call current weather, passing the model and callbacks. If it's initial, we do nothing, just unit. If it's error, we show an error component with title and description from string resources, a Lottie error animation from raw resources, and an onRetry callback that triggers the start event again to reload. Moving to current weather composable. This takes the weather model and callbacks and renders the actual content. We use lazy vertical grid with fixed 2 columns. This creates a grid layout that scrolls vertically. We set content padding and spacing between items. The first item spans the full width using grid item span with max line span. This is our hero weather section showing the main weather info with a search button. The second full span item is hourly weather section displaying the horizontal scrolling hourly forecast with the weekly button callback. Next, we use the items function to iterate through the weather details list. Each item has a key based on its title for efficient recomposition. The span is set to 1, so these take up single grid cells, 2 per row. Inside, we use a when expression to determine which detail component to render based on the sealed class type. After the grid items, another full span item for MoonPhaseItem showing the moon phases horizontally. Finally, a full span rain chance item displaying the 3-hour rain forecast. Let's set up the next feature by creating a new package inside the feature and naming it Future Forecast. Inside it, mirror the same structure we used for current ones. We're defining 3 sealed interfaces for MVI architecture. First is UI event. These represent user actions. We have one object onStart representing the screen initialization event. Next is UI effect. These represent one-time side effects like navigation or showing toasts. Currently empty but serves as the contract for future effects. Finally, UI state represents all possible UI states the screen can be in. We have 3 states here. Weak weather is a data class holding the successful state with weekly weather model containing forecast data. Loading is an object for the loading state when fetching data. Error is an object for the error state when something goes wrong. Forecast UI model. This is the top-level model representing the entire weekly forecast. It contains a list of daily forecast UI model objects with an empty list as default. Next, daily forecast UI model represents a single day's forecast. It has the day name as a string, weather icon resource ID as an integer, min and max temperature strings for display, and a list of hourly forecasts that defaults to empty. This nested structure lets us show both daily overview and drill down into hourly details. Finally, hourly forecast UI model contains detailed weather data for a specific hour. We have the time string for display. Rain information includes rain in mm as display string, rain amount as the raw double value, rain chance as both percentage string and double value for calculations. Humidity has the integer percentage and display string. Cloud cover has percentage integer and display value string. Pressure as integer and formatted string. Wind data includes wind direction angle as a float for rotating wind indicators and wind speed as a display string. This is an extension function on weekly weather forecast that transforms domain data into presentation-ready UI models. First, we define 3 nested helper functions. The time function converts epoch seconds to a display string. It takes the time and optional zone ID, creates an instant, converts to local date, compares with current date, if equal returns today, otherwise returns the day of week abbreviated like Monday or Tuesday. The getTime function converts the hour index to a 12-hour format with AM/PM, uses modulo 24 to handle hour wrapping. 0 becomes 12 AM, hours less than 12 add AM suffix, exactly 12 is 12 PM, anything else subtracts 12 and adds PM. The getWeatherIcon function maps weather codes to drawable resources. 0 is clear, 1 through 3 are cloudy variants, 45 and 48 are fog. Various ranges map to rain, snow, thunderstorm, or hail icons. Defaults to clear if code doesn't match. Now the main mapping logic. We map over daily data.values. Each daily forecast gets transformed. Inside, we map over hourly data with an index. For each hour, create hourly forecast UI model, time from getTime with index, rain amount using helper function with precipitation unit, rain chance as percentage string and raw value, humidity as integer percentage and display string, cloud cover similarly, pressure as integer and formatted with unit, wind direction as float angle, wind speed with unit, and raw rain amount. After mapping hourly data, create daily forecast UI model with day from time function, weather icon from code mapper, min and max temps rounded to int with temperature unit, and the hourly forecast list we just created. Finally, return forecast UI model wrapping the daily forecast list. The getRainAmount helper handles rain display logic. If rain is 0 or less, return an empty string. If less than 0.25, show less than 0.25 with the unit. Otherwise, show actual value with units. This mapper centralizes all formatting logic. This is a HILT view model annotated with HILT view model. Constructor uses @inject to receive getWeeklyWeather UseCase dependency. We create a private mutable state flow, initialized to the loading state. This holds our UI state internally. We also create a private mutable shared flow for effects, one-time events. We expose the state as a public state flow using as stateflow to make it read-only for the UI. The event function handles incoming UI events. It launches a coroutine in Viewmodel scope, so it's lifecycle aware and cancels when Viewmodel is cleared. Inside the when expression, we handle the onStart event. Call the use case, which returns a result type. We use fold to handle both success and failure cases. On failure, set state to error. On success, map the domain model to UI model using our toForecast UI model extension function, then wrap it in weak weather state. This follows unidirectional data flow. Events come in through the event function, trigger business logic in the use case, transform results, and emit new state. PercentageColumn, Composable creates an animated vertical bar chart column, takes percentage as double, time string, and display value string. First, convert percentage to integer, then animate the height using AnimatedProgressIndicator state. Animation spec uses spring with medium bouncy damping and low stiffness for a smooth elastic effect. Then create a column with center horizontal alignment and top vertical arrangement. The first element shows the display value text at the top using a small body type. Add a spacer for separation. Then create a fixed size box, 30 dp wide and 80 dp tall. This acts as the container with bottom center alignment so our bar grows upward from the bottom. Inside, place another box that fills width but uses our animated height. Apply rounded corners with 50 dp radius for pill shape. Background color comes from the helper function based on percentage. The getColor from percentage helper uses lerp, linear interpolation, to blend between two theme colors. The start color is composable, displays rainfall amount as a vertical bar with animated percentage. Takes time string, rain display string, rain amount as double, and rain percentage as integer. First, animate the percentage value using AnimatedIntoState, targeting the rain percentage. This creates a counting animation effect. Then create a column with bottom vertical arrangement so content aligns to bottom and center horizontal alignment. Display the rain amount string at top using body small text. Then create a box for the rain bar. Width is 30 dp, minimum height 4 dp, so it's always visible. Actual height is rain amount times 10 dp, so more rain equals taller bar. Background uses helper function to get color based on amount, another spacer below, then show the animated percentage with %sign using body medium type. Finally, display the time using the label small type. The getRainColor helper determines bar color based on rainfall. If rain amount is less than 0.25, return transparent, essentially no visible bar for trace amounts. Otherwise, calculate alpha dynamically. This composable displays wind direction as a rotating arrow icon with speed and time. Takes wind direction as float angle, wind speed string, and time string. First, animate the rotation using AnimateFloatAsState, targeting the wind direction angle. Uses spring animation with medium bouncy damping and low stiffness for smooth elastic rotation effect. Create a column with top vertical arrangement, fills width, and center horizontal alignment. Display the wind direction arrow image at 48 dp size with top padding. Apply a graphics layer to rotate it using our animated rotation value on the z-axis. Tint it with secondary theme color and set alpha to 0.7 for subtle translucency. Add spacer below, then show wind speed using body small text. Another spacer then displays the time using a label small type. This creates a compass-style wind indicator, where the arrow smoothly rotates to show wind direction while displaying the speed numerically. Create a new file named climatemetricscard.kt, then we'll build it step by step. This composable shows a selectable climate metric as animated bars over time, using a list of hourly forecast models. We start by declaring a remembered selected index with an initial value of 0. Next, define the options list as pairs of a label string and a drawable ID for humidity, cloud cover, and pressure. From that index, we derive the current title and icon. Wrap the whole UI in your generic info card, passing the dynamic title and icon, and put the rest inside the contents lambda. Inside the card, add a single choice segmented button row that fills the width and has a little bottom padding. Use for each indexed over options to create a segmented button for each metric. The selected state checks index against selected index. On-click updates selected index, and the shape comes from segmented button defaults with the button's index and the total count, so corners round correctly at the ends. Show each option's label with the label medium text style. Below the segment control, create a lazy row that fills the width and spaces items by 16 dp. Use items indexed over the hourly list and pick the numeric value based on the current selection. Humidity percent for 0, cloud cover for 1, pressure for 2, and 0 as a fallback. Build the matching display string the same way. For each hour, call your PercentageColumn component with the numeric value as a double, the display value string, and the hour's display time. Drop a new file into future forecast, composable/items, and name it rainchartcard.kt, then we'll wire it up. This composable shows hourly rainfall as a horizontal, scrollable chart. Wrap the content in generic info card, pass the title rain, and use your rain vector as the icon so the header is consistent with the rest of the UI. Inside the contents lambda, create a lazy row that fills the width and uses 16 dp spacing between items to keep the bars readable and evenly separated. Now feed the data. Use items on your hourly forecast list, and for each hour, call the rain item we built earlier. Pass the display time string, the rain amount in millimeters as a string for the label, the raw rain amount as a double for sizing the bar, and the rain chance as an integer for the percentage badge. We'll start by creating weather selectable infocard.kt under future forecast/composable/items. This composable renders a daily forecast card that can be tapped and visibly selected. It takes 3 inputs: a Boolean that tells us if this card is selected, a daily forecast model for the content, and an on-click callback. First, we derive the background color from the selection state. When selected, we use a brighter surface tint from material theme so the card pops. When not selected, we fall back to a dimmer surface tone. That color becomes the card's container color, and we wire on click to make the entire card interactive. Inside the card, a column fills the width, uses 8 dp padding, centers its children horizontally, and spaces elements in a tidy vertical stack. At the top, we show the day name with typography.bodysmall. For text and icon contrast, we call content color 4, card color, which automatically picks a readable foreground against whatever background we computed. After a small spacer, we display the weather icon at 50 dp to keep the visual weight balanced. Another spacer, then we print the temperature range as min degrees, max degrees with typography.labels small using the same derived content color so it stays legible in light and dark themes. The result is a compact, accessible card that clearly highlights the selected day. Tapping it triggers the callback to update selection in the parent, and that selection drives which day's hourly details show below. Start by adding wind speed and direction card.kt under future forecast/composable items, then we'll wire it up. This composable is a thin wrapper that presents hourly wind as a horizontal timeline. Wrap the UI in generic info card, set the title to wind speed and direction, and use your windy vector icon so the header matches the rest of the screen. Inside the card's contents lambda, place a lazy row that fills the width and uses 16 dp spacing between items to keep each hour readable. Feed it the hourly forecast list with items, and for every entry, call wind direction and speed item. Pass the formatted wind speed string for the label, the wind direction angle as a float so the arrow can rotate, and the display time string. The result is a simple scrollable card that lines up animated direction arrows with speed labels for each hour, giving a clear visual snapshot of wind patterns across the day. Let's create FutureForecastScreen.kt inside feature/FutureForecast and wire it up. In the screen composable, grab the Viewmodel with Hilt, collect its state with collectAsState, and immediately send the onStart event so we kick off the first load. Render by switching on the state with a when. If it's weak weather, call weak weather with the model. If it's loading, show the loading dialog using your Lottie raw resource. If it's error, show the error component with title and description from string resources, and pass a retry that fires onStart again. Now add a private weak weather composable next to it. It takes the weekly model and remembers a selected card index starting at 0 so we know which day to drill into. Lay out the screen with lazy vertical grid configured as a single column so it behaves like a list but still lets us span items. Fill the size, add padding on all sides, and use 16 dp vertical spacing with 8 dp horizontal spacing for clean rhythm. The first full span item is a centered title. Use a column to center text and show 7-day forecast with the display small style. The second full span item is a lazy row selector of daily cards. Use items indexed over the daily list, set selected on the card when its index matches selected card index, and update selected card index in onClick so tapping a card focuses that day. Below the selector, add 3 regular grid items that stack vertically in our 1-column grid. First, render rain card with the selected day's hourly list to plot the rain timeline. Next, render climate details card, which shows the segmented control for humidity, cloud cover, and pressure using the same hourly data. Finally, render wind speed and direction card to visualize speed and direction for that day's hours. This flow keeps the screen predictable. Pick a day at the top, then scan rain, climate details, and wind for that selection without extra navigation. Create a new file called homescreen.kt in the app module, then we'll wire up bottom navigation. We start with a private enum class home tab that defines our 3 tabs: home for today, weekly for week, and settings. Each entry carries a title string and a drawable ID for its icons so we can render labels and vectors consistently. Now add the home screen composable, annotate it for API level tiramisu, and accept a single navigate callback. Inside, remember the selected tab with an initial value of hometab.home. Use scaffold to get a standard layout and supply a bottom bar. Loop over the home tab entries and build a navigation bar item for each one. The icon uses vector resource with a content description, the label uses app text with the tab's title, selected checks if this item matches the current tab, and onClick sets selected to that tab. Scaffold passes inner padding to its content lambda. Wrap the body in a box that applies that padding so content sits above the bar. Switch on the selected tab with a when. For home, show current weather screen and pass 2 callbacks. The first sets selected to home tab.weekly to jump to the weekly view. The second calls navigate to open the manual location screen. For weekly, show future forecast screen. For settings, render settings screen and pass the same navigate function. We'll start by adding the home destination. Create a data object that implements your destination interface and points to the home route. With that in place, open Activity Viewmodel and switch the post-onboarding target. When the onboarding status becomes complete, set the next destination to home instead of settings so we land on the new bottom nav screen. Next, fix the 2 flows that still jump to settings. In manual location screen, find the launched effect that handles navigate to main screen and change the destination to home. Do the same in onboarding preference screen's launched effect so both paths align with the new entry point. If you see missing icons, that's expected during the walkthrough. The full icon set is included in the source repo, linked in the description, and it will resolve once you pull those assets. Let's run it. If hilt wiring is fine, but you hit a network logging error, open the network module and correct the provider signature. In Provide OKHTTP Client, use OKHTTP's HTTP logging interceptor type instead of a generic interceptor so the DI graph matches the actual binding. Rebuild, rerun, and you should drop straight into home after onboarding, with manual location and preferences both returning to the same place. Okay, so we have identified one more issue to fix. Jump into manual location viewmodel.kt and we'll wire the navigation. In the event handler, locate the save selected location branch. After you finish persisting the chosen place, emit a one-time effect to move to the main screen. Build and run. Tap select this location, the save completes, the effect fires, and you should arrive at home. If this series is helping, share it with a friend, hit like and subscribe so you don't miss the final part with the animated splash and analytics.